4 minutes and 20 seconds. That is the entire window between launch and impact. 4 minutes and 20 seconds from the moment a missile engine ignites in the deserts of central Iran to the moment its warhead strikes a target deep inside Israel. Not 10 minutes, not 15, just 4 minutes and 20 seconds. Imagine the sequence. A rocket motor roars to life somewhere far beyond the horizon. The plume rises violently into the sky, bright enough to be seen by satellites orbiting the Earth. Sensors detect the heat signature almost instantly. Within seconds, computers in multiple countries recognize the launch. But recognition is not the same as response. Because even though the detection happens quickly, the rest of the chain, the warnings, the calculations, the alarms, takes longer, much longer. Israel's National Missile Warning System, one of the most sophisticated civilian alert networks ever built, requires approximately 6 minutes to complete its full cycle. 6 minutes to detect a launch, confirm it, calculate the trajectory, determine where the missile will land, activate sirens in the right areas, and alert the population to take cover. 6 minutes from beginning to end. But the missile does not wait 6 minutes. It arrives in 4 minutes and 20 seconds. That means the warhead hits 1 minute and 40 seconds before the warning system can even finish telling people that danger is on the way. The missile responsible for this terrifying timeline carries a name. Iran calls it the Fattah-2. It is described as a hypersonic glide vehicle capable of traveling more than 1,400 kilometers at extraordinary speed. At peak velocity, the weapon reaches roughly Mach 15, 15 times the speed of sound. That translates to about 11,500 miles per hour, or roughly 3 miles every single second. Now consider the distance between Tehran and Tel Aviv, just under 1,000 miles. At 3 miles per second, the math becomes chillingly simple. A missile leaving central Iran can cross that entire distance in just over 4 minutes. 4 minutes and 20 seconds. No delay, no pause, no room for hesitation. Speed alone is frightening, but speed is only part of the problem. The real danger lies in how the missile moves. Traditional ballistic missiles follow a predictable arc. They rise high above the atmosphere, then fall back toward their target along a path that can be calculated with physics. Defensive systems rely on that predictability. Radar detects the missile. Computers calculate its path. Interceptors launch toward the point where the two objects should meet. If everything works correctly, the interceptor collides with the incoming warhead and destroys it before it reaches its destination. That process has worked, at least partially, for decades. But the Fattah-2 does not behave like a traditional ballistic missile. After its initial boost phase, the weapon separates from its rocket and begins gliding through the upper atmosphere. During this glide phase, small control surfaces adjust its direction continuously. The movements are subtle. 5 degrees left, 3 degrees right, a slight dip downward, a gentle climb. Each adjustment seems minor, almost insignificant, but those tiny changes mean the missile is never exactly where defensive systems expect it to be. And when something is traveling 15 times faster than sound, even a small deviation can translate into miles of difference. Miss by 3 degrees at Mach 15, and the interceptor may pass harmlessly through empty sky. Israel's layered missile defense network was designed to deal with different types of threats. High-altitude ballistic missiles are the responsibility of the Arrow system. Medium-range threats are handled by David's Sling. Short-range rockets and drones are intercepted by Iron Dome. Each layer was engineered for a specific type of incoming projectile. And for years, that layered approach worked well enough. But the new missile sits outside the envelope those systems were built to handle. Arrow interceptors are optimized for targets flying above 100 kilometers. The hypersonic glider spends most of its flight much lower, slipping through the atmosphere at altitudes where Arrow struggles to engage. David's Sling is designed for targets traveling around Mach 5 to Mach 8. The new weapon moves nearly twice that speed. Iron Dome was never meant to fight hypersonic vehicles at all. The result is an uncomfortable reality, not because the defensive technology is poorly designed, but because the threat has evolved faster than the defenses. Now imagine the timeline of an actual launch. Second 0. A mobile launcher in Iran fires the missile. The rocket ignites, pushing the weapon upward with enormous force. Within 3 seconds, early warning satellites detect the bright heat signature of the engine plume. That information is transmitted to command centers monitoring global missile activity. 10 seconds after launch, radar systems begin tracking the object. Computers immediately begin calculating its trajectory. Minute 1. The missile has already climbed to an altitude of 40 kilometers. Its speed is approaching Mach 10. Data from multiple sensors confirms the direction of travel. The trajectory indicates the missile is heading toward Israeli airspace. Air defense networks begin preparing possible responses. Minute 2. The rocket booster completes its job. The glide vehicle separates and begins descending. Velocity increases further, Mach 15. At this stage, interception is still theoretically possible. Commanders authorize the launch of defensive interceptors. 2 missiles streak upward from separate batteries. Their mission is to collide with the incoming weapon at a precisely calculated point in space, if the math holds. Minute 3. The hypersonic glider begins maneuvering. Small corrections to its flight path, not dramatic turns, just slight changes, but enough to disrupt the calculations guiding the interceptors. Radar systems update their tracking data continuously. Computers recalculate the intercept point, and the results become clear. The interceptors are heading toward a place where the missile will no longer be. They will miss. There is not enough time to launch another attempt. The incoming weapon is less than a minute away. Minute 4. Civil defense authorities activate warning sirens in the predicted impact area. People hear the alarms and begin running towards shelters. But movement takes time. Even the closest protected space may require a minute or more to reach. The missile, meanwhile, is already descending through 15 kilometers of altitude. Its speed remains extreme. Seconds later, the warhead detonates. The explosion arrives barely 20 seconds after the sirens begin to sound. For many people, the warning comes too late. They are still on the way to shelter when the impact occurs. The entire event, from launch to detonation, has lasted just 4 minutes and 20 seconds. Detection occurred, calculations occurred, defensive launches occurred, warnings were issued, yet none of it changed the outcome. The timeline was simply too short. For more than a decade, Israel's population lived with the understanding that missile defense could protect them. Not perfectly, but reliably enough. Iron Dome intercepted the majority of rockets launched from Gaza. Other systems handled longer-range threats, and the alert network provided civilians enough time to reach shelters. That structure created a sense of resilience. Life continued. Children went to school. Offices opened each morning. Cities functioned despite periodic attacks. But a 4-minute strike changes the equation. If the warning arrives after the explosion, the alert system loses its purpose. Shelters are only useful when people have time to reach them. Interceptors only work when they can predict where the target will be. When both assumptions fail, the entire defense model begins to unravel. Military planners understand this reality even if it is not discussed openly, because acknowledging it publicly would raise difficult questions. What happens when the next missile launches? How do you defend against something that arrives faster than the warning cycle itself? The challenge extends beyond civilian protection. It affects military decision-making as well. For years, strategic doctrine assumed that early warning would provide enough time to prepare retaliation before incoming missiles landed. Aircraft could scramble. Commanders could authorize strikes. Deterrence relied on the idea that any attack would immediately trigger a response. But when a missile arrives in 4 minutes, that timeline collapses. By the time commanders confirm the launch and begin issuing orders, the explosion may already have occurred. Retaliation still happens, but only after the damage is done. And that subtle difference changes the strategic balance. There is another complication: decision time. When radar detects a high-speed object approaching national airspace, leaders must quickly determine what kind of weapon it carries. Is it conventional or nuclear? Is it a single strike or the opening move of a larger attack? Those are decisions that normally require careful analysis, but hypersonic weapons compress that process dramatically. 4 minutes leaves almost no time for certainty, which increases the risk of catastrophic misjudgment. And this reality is not limited to one region. The technology behind hypersonic glide vehicles is spreading. Major powers are developing similar systems. Several countries have already tested them. Others are racing to catch up. Every nation that relies on missile defense systems built around longer warning times may eventually face the same challenge. Early warning networks were designed with the assumption that incoming threats would follow predictable paths. Hypersonic weapons challenge that assumption. They move faster, they maneuver more aggressively, and they shorten the window for every response. Detection, decision, interception, evacuation. Each step becomes compressed into seconds rather than minutes. 4 minutes and 20 seconds. Faster than the alert cycle. Faster than the interceptor calculations. Faster than human decision-making itself. In that narrow slice of time, the missile crosses an entire region, strikes its target, and disappears into history. And sometimes, the siren begins to sound only after the explosion has already happened.